Yeah, welcome back. We now want to look at counting techniques, all right? So counting techniques and then some combinations. So some concepts of counting and some methods of counting that are useful in probability theory. So fundamental counting rule is that in any sequence of n events, in which the first one has k1 possibilities, second event has k2 possibilities, third event has k3 possibilities, and so on. The total number of possibilities for such a sequence is k1 times k2 times k3 up to the end, all right? So up to the last event. So for example, if you have the event of tossing a coin and then rolling the dice, find the number of outcomes for the sequence of events. First of all, the possible outcomes from tossing a coin are 2, okay? And then if you roll a die, the possible outcomes are 6. So the total number of possible outcomes for the sequence of this event is 2 times 6, which is 12. Okay. Now, there is the factorial notation. It's a very important notation in counting techniques. You want to look at it. So suppose we have n distinct elements in a set. We want to know the number of ways these elements can be arranged in order. Now, the act of this arranging is called permuting, okay? Now, the number of ways that these elements can be arranged is the number of permutations of these n distinct elements. Now, let's note that when counting with permutation, the order that the items are arranged is important. So if there are elements where there are events A, B, and then there's B, A, if or this can represent anything, this can represent human beings, can represent objects. Now, when you arrange such that A comes before B, it's a different arrangement when B comes before A. So we consider these are two different arrangements, okay, instead of us considering them as one. All right. Now, to calculate the number of permutations, consider n elements that are in a particular bag. Draw elements one at a time. Take note that these elements are distinct. Each of them are unique. So, for example, the people in your classroom, students in your class, everyone is distinct. You don't have two of the same person in your class, okay? So how do you arrange such n distinct elements that are in a bag in some order, okay? So we'll start taking out the elements, if it's in a bag, we'll take them one by one until we redraw everything, okay? So since there are n choices, because we are considering n elements that are in the bag, how many ways can you choose can you make your first choice? With your first choice, there are n of these elements in there. So there are n different ways you can make your first choice, okay? After you've made that choice, you don't put it back. It is without replacement. So how many more are left after the first choice is made? There are now n minus 1 elements left. So you have n minus 1 ways of making your second choice. Then you move on, you have n minus 2 ways of making your third choice. And then you have n minus 3 ways of making your first choice. And so finally, you have just 2 ways of making your last but one choice. And then only one will be left. And that will be your last choice, okay? So we have n factorial. We represent this kind of sequence of making a choice as n factorial, which is being given as n ways of making the first choice. And then you have n minus 1 options. So you have n minus 1 ways of making your second choice. Then with n minus 2 more elements left, you have n minus 2 more ways of making your third choice until you've selected everything and you have just one more element, and that will be your last choice, okay? So for example, the notation n with this is read as n factorial. So for example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. 9 factorial is given as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Take note, 0 factorial is always equal to 1. It's the same as 1 factorial. 1 factorial is also always equal to 1. Another example, you are given 3 digits, 1, 2, and 3. Each digit can only be used once. Take note, these are distinct elements. If they can be used once, it means that you cannot replace them. How many different 3-digit numbers can be formed using these digits? How many 3 different digit numbers? For your first choice, how many options do you have? 3 of them. So you have 3 options. And then after you've made one choice, you will have only 2 left. We don't know which one it will be anyway, but you have only 2 left. So for your second choice, you have 2 options. After making the second choice, you have just 1 option left. So for your third choice, you have just 1 option. So you multiply this and then it gives you 3 factorial. It's represented as 3 factorial, which is equal to 6. Now, indeed, what we are saying is true, because if you really want to see how these 3 numbers can be, different 3-digit numbers can be formed from this, it's listed out here: 1, 2, 3, 1, 3, 2, and so on. And it's these are the only 6 ways you can form 3-digit numbers from these 3 figures. Okay. There are many more examples here you can explore for more understanding. Now let's look at the concept of permutation. Okay. I mentioned it earlier, but I want to look at it better in detail now. So the factorial function was used to calculate the number of permutations of n distinct elements. Okay, when you want to arrange all of those elements or select all of those elements. However, what if you want to select only k out of those n elements and use it for permutation? Okay, and permute those k elements. So the number of k permutations of n distinct elements is denoted as this, npk, which equals n times n minus 1 times all the way to n minus k plus 1, where k is less than or equal to n. So we have n permutation k as n factorial all over n minus k all factorial. So as an example, let us see. Number 1, a medical facility wishes to assign offices to its 3 top officials. One office will be for the CEO, another office will be for the medical director, and another will be for the HR manager. If the medical facility has 8 offices to choose from, how many possible ways can the program be set up? So this facility has 8 offices. It wants to choose 3 offices out of them. Yeah, we have 8 offices and we want to choose 3 offices out of them. Okay, so this is a question of permutation. Why is it so? It is so because we want to make these offices are distinct. There are 8 different offices, and we are choosing 3 out of them. And of these 3, these 3 that will be chosen will also be distinct. No office can be chosen twice, because once you choose an office, you can't choose it again. Okay, so that is why it is a question of permutation. So we can go straight ahead and then use the formula for permutation as 8, choose 3, and then we fix it in the formula and get our answer. Okay. There's another example here. You're given 4 letters, A, B, C, and then D. Each letter can be used only once. How many different 3-letter codes can be formed using these letters? So I want you to give this a try, and then you give me feedback in class. Now we move on to the concept of combinations. Okay. Now, permutations A, B, in other permutation, we consider these 2 arrangements, A, B, and then B, A. We counted them as 2 because they are distinct. But under combinations, we don't. Because once you select A and select B, it doesn't matter whether A was selected first or B was selected first. Under combinations, all that matters is that we selected A and then B, and it's in our hands or it's in a particular place. We don't take regard to the fact that A was first selected or B was first selected. So combinations looks at problems involving selections of distinct objects where there is no regard to order. Okay, so to calculate the number of k combinations of elements, you choose k elements from a bag of, say, containing n elements. It's an example. Now, after an element is chosen, you don't replace it. We are just concerned about which elements are selected. We are not concerned about the order in which those elements are selected. So the number of k combinations of n distinct elements is denoted as n combination k, okay, or n binom k. So this is read as n choose k. So to calculate n choose k, there are k factorial ways to arrange each set of k elements. Take note. Under permutation, we would have been particular about how if we selected this particular three groups, how are they arranged? So in the example we looked at regarding 8 offices, we were choosing three of these offices for these top 3 officials. We would have been concerned about, first of all, which of the 3 offices are being chosen. And then we're further concerned about which of these 3 that we have chosen is being given to the CEO, which one is being given to the managing director, and which one is being given to the HR manager. But in a combination, we are not concerned about that. All that matters to us is that which 3 are chosen. As to whether the CEO is in A or B or C is not considered at all under combination. All that matters is that which of the 3 are chosen, and that's it. So when order does not matter, each set is counted only once, okay? Whereas when order matters, each set is counted k factorial times to include every possible arrangement there. So we are saying that then n permutation k is the n combination k times k factorial, because n combination k just gives us the number of the ways of choosing, making the selections. But for an permutation, you want to also know how the order of how many, if you make a particular choice, what are the various ways you can arrange them also. The order in which you can arrange them, that's k factorial. The order in which you can arrange them, and that's k factorial. So we are saying that n choose k is equal to n pk all over k factorial, which is we divide both sides here by k factorial. And then further, we know that npk is n factorial over n minus k all factorial. So you simply multiply by the k factorial we have introduced there, given that k is less than or equal to n. Let's take note that under combinations, n choose k is the same as n choose n minus k. Okay. So, for example, there are 5 socks in a drawer. Choose any 2 socks. Look at that. Choose any 2 socks. Now calculate the number of possible pairs of socks that can be chosen. If you look at these socks, indeed, there are 5 different pairs of these socks, but this question is a combination question because this question is a question of combination because we want to choose any 2 socks. It doesn't matter to us whether we chose. In fact, the socks are not even labeled in the question. So it doesn't matter whether we choose A first or B first or socks number 3 first. All that matters is that we should choose any of the 2. Okay. So we are taking this as a combination question. So once we know that there are 5, we are choosing 2. You use the formula for combination and then you fix it. So if we label the socks as S1, S2 up to S5, then the 10 possible pairs of socks are S1 and S2, or S2 and S3, S3 and S4, and so forth. Realize that we didn't write S1 and S2, and then also write, under permutation, we would have written S1, S2, and also write S2, S1, because we consider them as different selections, because under permutation, order is important. But under combination, we wrote S1 and S2 without giving regard to also writing out S2 and S1, because once we choose these 2 sorts, S1 and S2, we've chosen S1 and S2, and that's all that matters to us under combination. All right, so these are the examples of the combination. In your own, as you read through, as you listen to these videos and read your notes, you can try your hands on them for deeper understanding. So this brings us to the end of the concepts of counting techniques. We will move on to random variables and then the probability distributions in our next session.